Catherine. Hi, everyone. We're excited for today's session on water innovations from space. I think we've got a pretty interesting, next hour ahead, and we're really going to be focusing on three main things. First, we're going to take you through just a really brief two-question Mentimeter quiz to get you thinking about what on earth we could be talking about today. We'll then go directly into the presentations by our two presenters, Eva Mladenova and Amber Jenkins. And then we really wanted to save a lot of time to be able to answer any of the questions that you might have for us. And so a large portion of today's session will be dedicated to just hearing from all of you. And so to start, I'll introduce myself. My name is Shana McLean. I work for NASA's Earth Sciences Division. And I serve a lot of roles, but essentially I'm the Global Partnerships Manager, and I advise the Earth Sciences Division on risk reduction and resilience. My background is in environmental science and water governance of international river basins, and so it's really exciting to be with all of you here virtually and to see such an energetic and exciting group of young professionals dedicated to water interests. And so it's really a pleasure to be able to participate in this event, and I'm appreciative of all of your attendance and excitement regarding our session. I am joined by my co-chair, Julianne. Julianne, would you like to introduce yourself?
Absolutely. Thank you, Shana. My name is Julianne. I think a lot of you have already seen me around this General Assembly over the last couple of days or even talked to me. I am the chair of the WYPW research group. So we're basically a small network within the larger World Youth Parliament for Water, connecting young researchers and enabling you to do all kinds of cool research. And I guess when it comes to cool research, we're exactly in the right session here. And so I am extremely excited to see what our colleagues or speakers from NASA will tell us today. And just so for you to know to interact a bit with the session, feel free to use the chat throughout to discuss, to ask questions. I will take note also of questions throughout the presentations. So we can really go into the discussion afterwards. And considering we have this translated in English and French, so make sure if you would like to hear this in French, to use the interpretation button. You can also absolutely ask your questions in the chat in French.
Excellent, thank you. So what we're going to do is just leap right into the Mentimeter questions. I'm going to share my screen and the questions that we'd like to ask you. Let's see. And can everybody see what I am sharing?
Yes, yeah, we can see.
Excellent. So for all of you, if you could please go to menti.com, I think it's also in the chat box for your help, and use the code 54627841. Please answer, give us some ideas of what you think of when you hear the word NASA. I can imagine already what a few of the words will likely come up as. Because I know when I was, I have a background in humanitarian action. I worked for a number of years with the UN before coming to NASA, and I was really surprised to find out what NASA did beyond what I knew of it, which was primarily what we're seeing up on this screen right now, which is space technology, satellites, rockets. In fact, one of my PhD advisors, when they heard I was going to NASA, said to me, "But you're not a rocket scientist. Like, why on earth are you going there?" But what I think is really cool about what we're going to be talking today, which I do not yet actually see on the screen, oh, I see it now, is Earth observation. So I'm going to maybe stop this in just a couple seconds as we get more words, and then turn it to the next question. So let's close the voting now for this one and move to our second question, where we are definitely going to be talking about Earth observation and the space components related to it. Let's now look at what your thoughts are when we talk about what you expect to possibly learn from today's session. So we will be talking about space, we'll be talking about Earth observations, but what do you think, what other things do you think we might be focusing on today? So same code, I believe, on menti.com. So I see a few good comments coming in. We're definitely, I think what will be interesting about today is that it's probably going to be a blend of all the things that I see on the screen so far. I'll allow a little bit more time to get further input, and then we'll close before going right over to our presenters.
Anna, I don't think we can see the word cloud.
Oh,
your screen is a bit stuck.
Oh, well, that's sad.
Maybe if you just unshare and reshare it.
Stop sharing. Okay.
Of course, we want to see what all the participants think as well.
Yeah, I know. That's a good point. Okay, let's see. Share. Can you see it now?
Yeah.
Oh, perfect. Yes.
Excellent.
Not destroying other planets. I like that one.
Yeah, I know. I was just going to comment on it.
Can we confirm that NASA is in fact not working on the Death Star?
It's not. Okay. Well, I think it's about time to close anyways, but I will say this is definitely an interesting grouping of words. We're definitely going to be talking about connections in water and space, the environment, specifically on issues related to the food insecurity and water. And so let's see, I'm going to stop sharing my screen. We can definitely tackle the not destroy other planets element at another time or possibly later in the Q&A discussion, but that will not be the focus of today's presentations. So it's really great to hear from all of you. And we will now turn it over to our two presenters today. Our first speaker is going to be Eva Mladenova. Eva, why don't I turn the floor over to you? Please introduce yourself. Thank you so much.
Hello, can you see my screen? I just shared my presentation.
Yes.
It's in full screen mode, I hope.
Yes.
Hello, everybody. So a little bit about me before I start with my presentation. I am currently crop assessment analyst at US Department of Agriculture, Foreign Agricultural Services. It's been a long road until I got where I'm at the moment, and I love every single stage of my career. I will discuss in a little bit more details of how I got where I'm at today. I'm a hydrologist by training who studies water on Earth using satellite systems, and that became clear it's going to be the focus of the session today. So I was lucky enough to gain hands-on experience and practice in the field pretty much everything we were taught in class. I've installed rain and stream gauges. I've helped build a soil moisture network, measured subflow and snow depth, anything related to the hydrologic cycle, you name it, I've done it. And I did initially using station observations. Later on, a professor of mine opened the doors to remote sensing for me. So a professor of mine said that there's simply not enough instruments and gadgets on Earth that can help address all of the questions a hydrologist would want to answer. So try to figure out how much water there is in the Dolomites area in Italy or in the Sierras here in the US. Or try to generate a global soil moisture map that is equally understandable and useful for a farmer in Iowa and for for meteorologists. So I ended up focusing my career on the latter, and large portion of my talk will be focused on soil moisture. its importance, why do we need to monitor regularly, and what is the best way to do it. Now, soil moisture, like all of the rest of the components from the of the water cycle, can be monitored using various in situ-based instruments, and I'm sure you're aware of that. In situ-based monitoring is really good because it's as accurate as possible. However, it's expensive to maintain. And furthermore, how can we cover a very large area of the globe with instruments? It's pretty much not feasible. A few decades ago, a small group of very enthusiastic scientists suggested, what if we do that from space? And then in time, this became possible and became reality. And nowadays, there is a fleet of satellites, many of which are part of a project called the Earth Observing System, which constantly monitors the Earth's surface, biosphere, solid Earth atmosphere, and oceans. And here's an example of NASA's Earth Observing Satellite missions. And all of these missions collectively have gathered a spectacular amount of observations that can characterize pretty much any environmental variable. I'm pretty certain you've seen a version of this slide. So soil moisture is about 0.001% of the total water on Earth. And although this thin layer of soil may seem insignificant when compared to the total amount of water on Earth, it is this thin soil layer that controls the success of agriculture, regulates the partitioning of water between runoff and groundwater storage, impacts the distribution and growth of vegetation, movement of nutrients through the soil profile, and furthermore, soil moisture content is one of the very few directly observable variables from the hydrologic cycle that plays a very important role in the weather and energy budgets for climate studies. So let's dip a little bit deeper into what soil moisture is. It means different things to different people. In very general terms, soil moisture is the water contained in the soil above the water table, but I've included here a few more definitions. Soil moisture, a farmer's concept of soil moisture is very different than what a water resource engineer understands or a forecaster understands by soil moisture. Now, farmer's perspective. A farmer wants to know, is there enough water for my crop to grow and develop properly so that I can get maximum return on my investment? And if the farmer has access to irrigation water, then the next thing he would ask, when and how much do I irrigate? Here is an illustration of soil water holding capacity. There are two lines here that are important. First is the wilting point, and then we have this, the field capacity line. Now, the water below the wilting point is not accessible to plants. At that point, water is insufficient for plant growth, and we're talking about drought. The field capacity line, on the other hand, is when soil holds as much water as possible given its physical properties, and there is very little downward movement due to gravity and very little suction due to capillary action. Once all the pore space between the soil particles is filled, then we're talking about floods. Both floods and droughts can be devastating for agriculture, can cause significant yield losses, and of course, loss for the farmer. So this is the water between these two lines that is available to plants, and this is the amount of water that a farmer wants to know how much is it there and is it sufficient for my crops to grow. There are different ways to monitor soil moisture. I've summarized the 4 basic approaches. So we have direct measurements using in situ networks, hydrologic modeling, remote sensing, and of course, because these 3 are not enough, there are different ways to combine these 3. The previous 3 approaches, I will briefly discuss each of these in my next few slides, but while I'm discussing them, think about depending on the end user, what the requirements of the end user will be. And there are a few things to be considered in that regard: spatial resolution and coverage, accuracy, temporal resolution, depth, and so on. So starting with remote sensing. Remote sensing is an all-weather technique that has a day-round capability. It can provide global coverage, which is important. So, and aside from the global coverage, it can provide data at a very low cost that can be publicly available. Microwaves have the capability to penetrate through the atmosphere, through the vegetation layer, and measure the amount of water within that soil profile that's essential for numerous applications. There are two ways to monitor the soil moisture, using active systems or passive, which are illustrated here. The main difference between these two is the source of energy. In the active case, we have an energy source on the instrument itself, and then the instrument measures the signal that is sent back to the instrument, while in the passive case, the source of energy is the sun. So another big difference that's important for various different applications is the resolution. In the active case here, the resolution of the final product can be in the order of centimeters or meters, versus the active case, it's more in the kilometers. So when it comes to agriculture, 25-kilometer product may not be the best choice here. In 2010, soil moisture became or was recognized as an essential climate variable, and that sparked a big interest in generating global soil moisture products. Here is a list and illustration of some of the major missions used to develop global soil moisture products. On top, in the orange yellowish color, we have passive system. On the bottom, we have active, and right here in the middle is SMAP. I will very briefly focus on that mission. SMAP is an L-band mission. L-band is considered optimal for soil moisture monitoring because it's the least sensitive to the particles within the atmosphere, least sensitive to clouds, least sensitive to vegetation, and so on. SMAP stands for soil moisture active passive. Why is this mission different? Because it's the first mission that provides soil moisture information in various different spatial resolutions ranging between 3 kilometers and 36 kilometers. And on top of that, this mission has a very well-developed applications plan. Here is a list of the application areas. I've circled agricultural productivity because this is the area I'm involved with. But you see that soil moisture observations can be used for very different applications, including weather and climate forecasting, human health, national security, you name it, soil moisture apparently is important. Then hydrologic modeling and hybrid approaches. I'm sure you all are familiar with hydrologic modeling, so I will not spend a lot of time discussing what a hydrologic model is. Hydrologic modeling traces back to 1850, when Mulvaney developed a method for computing time of concentration and peak discharge. And then about the same time, Darcy in 1856 developed his Darcy law, which laid the foundation of quantitative groundwater hydrology. Then in the 1960s, they witnessed people at the time witnessed the birth of computer revolution and hydrologic modeling. So hydrologic modeling became a lot more sophisticated. Pretty much any component of the water cycle can be modeled and represented. But one big shortcoming of hydrologic modeling is that the output from the model is as good as the quality of the precipitation data. So if you have not so good precipitation data or forcing data, then of course, in terms of soil moisture, the accuracy of the soil moisture product would not be good. One way to account for these inaccuracies is to apply hybrid approaches, and one example is given here. We're talking about data simulation. Data simulation, in a nutshell, means merging different data sets. We can incorporate satellite or station data, which are independent from the hydrologic model, within the model using approaches such as the ensemble-Kalman filter technique illustrated here. A good thing of the ensemble-Kalman technique or any other data simulation approach is that it doesn't assume that the model is superior over the satellite observation or vice versa. The merging of these two is based on certain error characteristics, and it acknowledges that there is no perfect observation system. Well, major part of my career was focused on the development of microwave-based soil moisture products, their validation, development of hydrologic models, and so on. At some point, I realized that there are too many soil moisture products out there, but there is no real-life decision support system that uses these observations. And then with SMAP on the horizon, I got involved with a project that aims at enhancing the US Department Foreign Agricultural Services decision support system by improving its soil moisture information. USDA soil moisture is developed using the Palmer model, which is right here. I'm sure you're all familiar with the Palmer Drought Severity Index. The Palmer model is a very simple bookkeeping hydrologic model. It has only 2 layers, and is driven in this case by precipitation and temperature provided by the US Air Force. The US Air Force data has its issues, and they've been well known to USDA for a while. So what our goal was is to correct for these inaccuracies, and we did that by integrating satellite observations from various different systems. The latest development is the one that is based on integration of observations from SMAP. This is done using the ensemble common filter technique I described in the previous slide, and the output from the system is listed here in the middle. You see there are different soil moisture products, different levels. Each of these products provides different aspect of the soil moisture content that is useful for interpretation of vegetation status, yield formation, and so on. Data is then pushed to Crop Explorer. This is the USDA's interface where all of the agricultural and meteorological data related to agriculture is displayed, but also data is pushed to Google Earth Engine, where it can be used for other applications or for research purposes. It's been a long collaboration between various different institutions. On one side is USDA Foreign Agricultural Services, on the other side is NASA, and so on. As I said, the data is available for public use. How do we know that it works? Here is an example from the 2016-17 drought in South Africa. The drought was, I'm sorry, apologies for this. Okay, so the drought was most severe over the Western Cape. This is the southernmost province of South Africa. It's the country's largest wheat growing area. Wheat is grown between May and then harvested in October. The area has been experiencing decline in rainfall since 2015, but reached record low rainfall amounts accompanied by high temperatures and high evapotranspiration rates during the 2017 growing season. This slide can be split into 2 halves. So on top we have the 2016 growing season, and on the bottom we have the 2017 growing season. And then each half can be split again into 2 sub-halves. So on top we have the satellite improved model run, where we have SMAP ingested within the model. And then on the bottom we have the output from the model alone. One thing we see right away is the difference between what the improved run shows and what the model shows. So very obvious is, for example, for May of 2016, June of 2016, then October of 2017. And one other thing we see right away is this big green bullseye visible in the output from the model alone. Again, how do we know? Validation at global scale is not straightforward. It's not easy. So starting from the right-hand side of the image here, we have the 4 soil moisture maps. First, we have the satellite improved output, and then we have the output from the model. Again, they're very different. This is a zoom of only the output from May 2016 and October of 2017. The model is quite dry and very orangey kind of, and towards the red-orange spectrum of the scale bar. You see that this consistent kind of dryness throughout the model is in agreement with what the precipitation data says. So this is the southernmost tip of South Africa. On the other hand, the satellite improve output shows a very different variability. What we did here, we looked at what alternative precipitation data sets show. Plotted right in the middle is the output from chirps, and then the model, the satellite enhanced output is consistent with the distribution and variability captured in the rainfall, which gives us, in the chirps rainfall, which gives us confidence that SMAP has this additional information and is capable to correct for the inaccuracies inherent in the US Air Force data set. That small bullseye we see in the output from the model, it's a precipitation artifact. So this is technically a ground rain gauge data. The way how the US Air Force precipitation product is done is by merging different various sources. But because the merging technique is not most likely the best, the station looks like an isolated, or the precipitation captured by the station is like an isolated event. Again, SMAP sees that precipitation event is and is capable to correct for that Bose precipitation artifact, and the output is consistent with what another alternative precipitation data shows. In this case is the South Africa wetland surface data. Now, in summary, so currently there is an abundance of hydrologic related data sets, but there are not really that many well-developed applications that meet the end users and needs. And it doesn't matter whether you're a scientist, researcher, applications developer. What is important is to know what the end user's needs are, be capable to translate that data, extract the useful information depending on the end user, so that the data that is out there can have social impact. I'll stop here and then pass the screen back to Shannon. I'll be happy to answer your questions once we get to that part of the session.
Excellent. Thanks so much, Eva. So just to highlight a few points that she made, not only did you learn a little bit about our satellite mission on soil moisture, but a real key takeaway here is, of course, that in order to really get good modeled outputs, we need a lot of good comprehensive data, and not just on the front end side, but also to be able to validate whatever models we're developing, so that we can transition then from the data and the data products to supporting decisions. And that process isn't always very clear, right? I mean, we can't just give someone a data product and have them magically understand what exactly is being told to them. So translation becomes a large portion of our responsibilities when it comes to product development and supporting decisions in an applications perspective. And so it's a perfect segue to our next presenter, Amber Jenkins, who's going to be talking about how to take the science and turn it into decision making. So with that, I'm going to turn it over to you. Amber, the floor is yours.
Thanks, everyone. I really appreciate your time. I'm excited to engage with you and learn from you, and thanks for having me. So I'll just share my screen, my slides, and okay. Okay, can everyone see my slides?
Yes.
Okay, great. Thank you. Thanks so much for having me. My name's Amber Jenkins. I work with NASA's Western Water Applications Office, or WWAO. There's lots of acronyms in NASA. So WAO, as we call ourselves. And we work within NASA's Applied Science Program. And we really are a concerted effort to move water data, tools and technology within NASA to the hands of decision makers to really have impact on the ground. So before I dive in, I'll just say a little bit about me. I've been with NASA for over a decade. I'm based at JPL, Jet Propulsion Lab. I work for the Water Office, as I said, right now in strategic communications, program management, different initiatives. And it's really where the rubber hits the road. I'm really excited to be working with that office in that applied science unit. Prior to that, I managed the JPL Climate Center and co-founded NASA's climate change website, which has grown from strength to strength and won different awards and has been just a really nice thing for NASA to work with others on. Before that, I'm not a hydrologist at all or a space scientist. I'm actually a physicist, and I was a particle physicist for a number of years and did research into the Higgs boson a long time ago, and moved from that into science communication and really sharing my love of science and the passion that I have for what science can do with others. So I was in communication publishing for a while, worked with Nature magazine as an editor, founded one of their magazines on photonics, which is all about the science and technology of light, and then moved to NASA from that. So I'm a bit of a jack of all trades, but I'm really passionate about the power of science and technology to change our world. In fact, it changes our lives all the time, and how we can use that power to benefit society in different ways. And one of the things I really care deeply about is how we can tackle the climate crisis that we currently face. So I'll just go through, I can move my slides, which are stuck. There we go. So today I'm going to talk to you about a few different things. I'll give you a whistle-stop tour of what we do at the WWAO, the Water Applications Office at NASA. I want to start by talking about the power of perspective and why that is so important, what we see when we step back from the planet. Then I'll talk about how we try to see how we can get that information into an actionable form for decision makers on the ground. And I'll go through the different ingredients for success for how you do that, or what we've learned about how you can do that. It involves building careful and close and sustained partnerships. It involves then building custom solutions based on those partners and what they need. And throughout all, we have to focus on what impact we're having, how we measure that impact, and how we transition or move or transfer that solution, that technology, whatever it might be, out of NASA to the hands of the people that need it the most. Okay, so let's begin. So the power of perspective, this is our home planet, our beautiful blue marble, the pale blue dot. As Carl Sagan said, the only home we've ever known. And I wanted to just read a quote from Fred Hoyle, who's an astronomer. He said, "Once a photo of Earth taken from outside is available, once our sheer isolation is known, a new idea as powerful as any will be let loose." And I think that's really true, and as true today as ever before. When you see our planet from outside, when we ventured out into space and looked back, it was a very humbling experience. We realized how alone we are in that deep, dark cosmos, how small our planet is and how fragile it is, and how there are no borders from space, how pollution at one side of the globe travels straight to the other side of the globe, and how we really, really are all interconnected. And so this was a really powerful moment in our history and helped take us along the path to revolutionizing how we understand our home planet, how we take the pulse of our planet, and how we see our place on our world and in the universe. So as Eva mentioned, we have a whole suite of satellites that monitor the pulse of our planet. We also have airborne platforms. We take measurements from the ground. We use computer models. We have a whole suite of tools at our disposal, and they let you see beautiful things. And I just wanted to flash a few pretty pictures on the screen, because there are some great pictures that you get from a distance from that perspective. And this is just images of a glacier carving out over the land. You can see how water comes into the land, bringing with it sediment and life. You can see how huge, majestic ice shelves are carved up as our planet changes. You can see the intricate web of life and how water underpins beautiful wetlands and ecosystems around the globe. You can see how we are literally terraforming our planet. We change the face of the earth for food, for energy, for homes, for control. And you can see these things from space in very dramatic ways. So the power of perspective really helps us step back and see the wood for the trees and take a bigger picture. The question is, with all that knowledge, there is power, and how do we put that power into action? How do we give those data to those who need it most to have good impacts on decision making, and specifically within water? So we focus on water challenges in the Western US, and there are a number of them. So in the Western US, the arid US, we're faced with falling groundwater levels, diminishing snowpacks, increased natural disasters, storms, droughts, and floods, increased uncertainty about future water supplies. And in the face of all of these, we have growing populations, growing demand, and climate change. And so there's a lot of challenges that water managers have to face on an ongoing basis. And NASA can really play a role in providing data and tools and technology that could help enable those managers on the ground to make better decisions. So this is why we set up NASA's Western Water Applications Office a few years ago. And really our motto is that we deliver tools for managing a precious resource, that life-giving resource of water. So our mission is to improve how water is managed by getting NASA data, technology and tools into the hands of Western water managers. And the picture on the right shows you the purview, or the area that we look over and we interact with, and we try to gauge the needs of and then deliver solutions to. And this cog diagram here just kind of implies how WWAO fits in with NASA and the bigger picture of our sensors and data, and then interacts also with water managers to translate that data into things that they might be able to make use of. So how do we do this? Well, we take a three kind of stage process, although these steps are very iterative and kind of overlap. So on the left, we identify needs. So we build relationships with stakeholders throughout the West, and there are many. It is a very fragmented network at the federal level, the state level, the local level. And so we have to develop partnerships with those stakeholders to then identify what they need the most, what issues they're facing, what are the highest priorities for them, and where we might really be able to plug a gap. So we conduct systematic and in-depth assessments to identify those water needs, and we actually do this on a basin by basin pretty much basis across the West. And then we catalogue those needs and we share them with our scientists, with our partners, and build on those needs in a systematic way. Once we've identified needs that water managers have, we then work to deliver projects and solutions that might meet those needs. So we have to catalogue and collect NASA capabilities that may be useful and may be a match. So we have to match those needs to those NASA abilities. And then from there, we have to take a very careful and painstaking approach to build needs-driven projects and activities that might answer the call to filling those gaps. And then finally, and throughout this process, we have to think about off-ramp. So I've used the word transition, I use the word off-ramp. It's basically about how we build these solutions and then we hand them off to the partner that's going to use those solutions on a long-term and sustainable basis. NASA wants to be a partner in helping these things happen, but they don't want to own it forever. They want the partner agencies to be committed to using them, and we want to help move along the path from research to operations. And so we do this in various ways. We have transition plans from the get-go of the projects, and we're establishing a research to operations community at a kind of interagency level. So let's talk about that first prong, which is building partnerships and why that's so critical. So I've tried to underline up to now that stakeholder engagement is key. If you don't engage with the people on the ground and the people making decisions, then you don't understand what their needs are. You have to ask the right questions of the right people, and you can't just bulldoze your way in and think that you know what they need and think that if you build it, they will come. It's really about partnership building process, and it's really where hard science meets soft science. We are trying to deliver technical products and solutions, but totally key to all this process is delivering relationships that last, which are involving trust, communication, and really listening to one another. And so stakeholder engagement is a key part of what we've tried to innovate on at WWAO. So as I mentioned, we have to identify what the water managers need in the West. And we do this, here's a basin map here just showing how we kind of systematize our process. We actually have a multi-step process to collecting needs, and we do it basin by basin or region by region. So we start by partnering with a local organization in the region and doing a survey of the stakeholders involved. And sorry, my computer is a little. Can you still see my screen? I had an update that just flashed in front of me. Sorry about that. So we systematize our kind of measuring of needs across these basins. We do it with a survey, and then we do it with in-person workshops. And obviously that's been something that's been affected by the last year of COVID. But we dig into the needs and we build detailed use cases of what water managers need, the decisions they're trying to make, how they make them right now, and how they might make them in the future with additional tools or knowledge. So we collect these needs, we flesh them out, and then we rank them and prioritize them and try to iterate with partners. So this is just a quick snapshot of our water portal that we've recently launched. And you can find this at the link below. So we built a portal to collect and catalogue all of these needs that we've actually collected and our capabilities, NASA's abilities to answer some of these calls. And so water managers can come here and browse some of our relevant data products, and scientists can come here, and NASA's applied scientists and others can come here and look at what needs might be things that they could fill with the technical capabilities that they have. And so this portal is really the beginning of a dialogue that WWAO will be involved in with the water manager on one hand and the scientists who might answer those needs on the other. So now let's move on to the projects and the solutions that we try to deliver to solve some of these water issues that managers are facing. So I said that we're really about carving a path from research to operations, and it's not a simple or easy thing to do. It's far from trivial. So with this diagram, it's quite busy, but I'll just go through it quickly. There are multiple phases to the life cycle of the projects that we build. We have an idea. On the left here, you see concept, and we have to drive that idea from the needs that we get from our water managers. Then we design an application or a solution that might meet that need. We develop it, we build it, we implement it, we have to test it, we have to validate it, and we have to see if it can actually be implemented in an operational setting. And then all along this process, from the very beginning, we have to think about how are we going to off-ramp or transition out this solution to the water partner. And that's a really hard nut to crack, and it's something we have innovated on, but it's hard for a lot of people, a lot of agencies. So our end goal, as I mentioned, is sustainable operational applications that are being used in water decisions. And at the bottom, here are just some activities that we do to support this, what we call research to operations, or R2O process. So we measure impact from the beginning. We help support the projects with technology transition and business case analyses. We do market analyses to see if there is a market for the product that's being developed or the solution that's being delivered. And throughout, we are working with our partners across different levels of water management to build a community and build best practices for how you really push from science to action and how you get these data out into an operational setting. So I'll just give you a couple of examples I'll run through of areas that we focused on. We focused on a number of things, and we have a number of projects in our portfolio, but this is just one, and it focuses on snowmelt. Now, around the world, 2 billion people rely on snowmelt for water. And as the planet warms, water managers have to adapt to those changing snow levels, and that's extremely challenging. So better snowpack data is needed really around the world, but in the basins that we've assessed in the West, and they've told us in the Colorado, the Columbia, and the Missouri River basins, of the ones we've assessed so far, they've all raised that as the need for better snowpack data. So NASA has a number of options for helping with snow data, but one I'm highlighting here is NASA's Airborne Snow Observatory. So it basically showed that LiDAR and spectrometer can be combined to help forecast the amount of water in the snow water equivalent in mountain snowpack up to 98% accurately. And so what WWAO has helped do is give this research a nudge and fund projects that have established operational pathways to see how this snow data could improve runoff forecasts for managers in the West. And in 2020, this NASA Airborne Snow Observatory was actually spun off into the private sector, something of a real success story, talking about this path from research to operations. It is now in the private sector, and it delivered snow water equivalent estimates to various partners, California, Colorado, the US Bureau of Reclamation. And as a private entity, a private sector entity, ASO Inc. can outreach and to various bodies that NASA may not, and outreach to Congress has led to actual funding bills last year that were put through to actually devise a snow water supply forecasting program with funding for NASA, for ASO to continue this work. Another area in which we work is drought. Drought is a huge issue in the US, in the Western US. And this just highlights a project we've done with the Navajo Nation. The Navajo Nation face frequent and severe droughts. About 80% of homes don't actually have running water. And one of the issues with drought monitoring in that region is that they don't have the spatial detail in their data, and they don't have consistent measurements. So what we've done is helped them integrate satellite observations into their decision-making, essentially. We've combined satellite data with rain gauge data that they take on the ground, which is few and far between, about 85 rain gauges. And then we've built a tool called the Drought Severity Tool that produces on the fly maps of drought severity, for example, like the one you see at the bottom here in this slide, and really kind of pinpoints where the drought is severest and helps the Navajo managers essentially allocate relief where it's needed the most when drought hits. So this tool transitioned out to the Navajo late last year. this year, and it remains a sustainable application as a spin-off of Climate Engine with support from the Desert Research Institute. And part of our transition work with any of these projects is capacity building and training, which has to be done on an ongoing basis. And so we've done a lot of those with the Navajo, and some of that work and application work continues. Finally, I'll just talk about water for food. You can't really grow food without water. And so it's a huge area of focus and potential where NASA could help farmers essentially monitor the water they use, maybe grow more crop per drop, and understand field conditions better. And I know Eva touched on this in her soil moisture work. So in the Western US, agriculture can be the largest consumer of water. And so there's a real need, as I mentioned, to manage irrigation in better ways and get more information about that. So NASA has a number of ways that we can provide data to potentially manage agricultural water better, satellite-based irrigation management, soil moisture maps, as Eva mentioned, other things like fallowed land maps. And so this is just one example of another application that we are working on spinning off. We're using satellite data to incorporate into a decision tool, Crop Manage, that farmers and growers are using in the West to support farm irrigation. And actually, the trials and the results are showing that you can grow crops with no drop in yield or quality, saving about 20 to 40% of water, depending on the crop. And this tool is providing farmers with actually more than 3,000 irrigation recommendations a month. And the work is essentially going to be extended to probably 17 Western states. And that's one key thing that we look for in these projects. Can they be scalable? Are we offering a solution that may start in one state or one region, but could be scaled up to a number of other regions? So finally, I'll talk about impact and transition. And these are non-trivial things to do. How do we measure how well we're doing? You cannot manage what you don't measure. And how do we transition out that science to decision makers on the ground? So we've learned a lot of lessons, and I don't have time to go into all of it. And it's a work in progress. But transition planning is really something that has to begin when the project begins. It's not an afterthought. Transition planning needs to happen when the project starts. When you conceive of an idea and you work out how you're going to deliver a solution to a decision maker, you need to think about how that decision maker is going to ultimately own that ability at the end of the day, or the end of the number of years of work it will require. And that planning and work with the partner should be engaged and iterative between the scientists and the stakeholders. The stakeholders have to be committed to that transition. And we ask for things like in-kind contributions. We ask for a level of commitment because that reflects how committed they are to a sustained solution going forward. And we must have tangible goals for transition. Again, I'll go back to my comment. You cannot just assume build it and they will come. You have to have a real mapped out plan of how you will build it, and it will be passed on in useful ways. So for a successful roll-off or transition, the partner needs to be able to sustain that solution and independently operate it on a long-term basis. And to make this transition successful, trust, I'll come back to relationships, trust and long-standing relationships between the scientist and the partner are critical. And technology transition takes time. It's not an afterthought. It's not a small job. And this last slide here just shows you an example. Don't worry about all the words on it. It shows you an example timeline of that airborne snow observatory example, that snowpack survey work I talked about earlier. It took 10 years from the first discussions about technology with partners to get it transitioned out to the water sector. And that was arguably one of, it's been a real success story for NASA, and it's taken a long time. And so you cannot expect that this will happen in 2 years, or a project will be funded for 2 years and it will be rolled out and successfully picked up by the partner. So this is a difficult nut to crack, and there is no one way to do it or to transition a technology. So I'll just give you a few take-home messages. Our history is written in water, and our future likely will be too. Science matters, so find a way to make it count. Data and technology can drive better decisions, and NASA can help. Relationships, trust, and mutual goals are all crucial for translating science into action. And together we're writing the future of the planet, so let's work together to write the future that we want to see. Thank you.
Excellent. Thank you so much to both our speakers, Eva and Amber. Let's turn now over to Julianne, who's going to help us navigate some of the questions that we've seen arise in the chat box. Julianne, over to you.
Yes, thank you. And thank you, Ivor and Amber, for these insights. There are indeed a couple of questions that already came up in the chat during the two presentations. If you have more questions, everyone just throw them in the chat as well, and I will monitor them as they come in. To start with, we now heard a lot about these different applications of NASA technology, of remote sensing. How applicable are these in other cases than, for example, the Western US or South Africa? So how about rural populations in low-income countries? How expensive is it to really work with this technology? Is there a certain technological framework that you already need to have in place? What kind of knowledge do you need as a person to use this? And how can organizations like NASA assist with that? And I think I would direct that to Amber mainly, considering you're very much working with these partnerships. But maybe if you want to jump in also to Shana, because I know you're working a lot with regards to disaster risk reduction, humanitarian action, where those kind of countries are also very, very relevant.
Yeah, Shana, do you want to hop on first?
Go ahead, Amber. I'll take it. I'll take it after you.
So I'm trying to understand the question. The question is, how do we get the data into the hands of people in rural areas? Is that the question?
Yes, especially low-income countries.
It's very hard. It's, I mean, the work that we do is focused on the Western US by design at this point. Not that we couldn't focus on other areas, but it's a huge area to focus on and see what we can learn and expand from. And we've worked with, disadvantaged community. I mean, the Navajo Nation drought tool I talked about there, it's, we've worked with disadvantaged communities to try to deliver tools. I think these are questions that have to be asked from the outset. There's no one way to ensure success. And even when you do everything I talked about and tick every box, it still might not be able to be owned by that entity, that person, that partner. So it's very hard to do. You have to really partner. Those relationships are so important because you have to understand where the end user or the partner, I hate the word end user because they're really a partner, where they're coming from. So is it about data accessibility issues? Is it about data format issues? Is it about them worrying that the NASA data will go away when the satellite stops working? Is it that they need to get buy-in from other people around them, how to integrate this and change the way they make that decision right now, whether it be through a tool or a framework or a piece of infrastructure? So there's no one answer I can give as to what to do. I think we have the power to impact a lot of communities, rural, urban, different challenges in different areas of the world, and we're doing that across our program in different areas. But it comes down to understanding the unique needs of that stakeholder, and that takes time and that takes energy, and you have to be in it to win it. You have to be committed to intentional impact, otherwise you may not get the outcome that you want at the end.
So I'll just feed off of what Amber said. Partnership is really crucial here, and really even in her last slide, like NASA can help, but we're not the sole solution, right? And so I work a lot in, as the Global Partnerships Manager, I manage a lot of partnerships that are international. And so we've got partnerships with Conservation International, where we're developing freshwater health indices in the Mekong and Okavango River basins. But to touch on both Eva and Amber's point, a lot of the work that we do is intended to scale and to be transferable in other contexts. And so while we may be working in the Mekong, we're working on also being able to take these technologies and use them in other locations. But every time you do that, it requires further analysis, further processing, because you're looking for more unique or localized solutions. And so partnerships are definitely a key element of being able to not only get into focused solutions for the country, but then to decide what level of focus we're working at as well. So we've got other entities within NASA, such as the SERVIR program, which is another type of consortium similar to WWAO, where Amber works, where they're working in countries. There's 5 different hubs around different parts of the world that are working to, usually at the national level, that can look specifically at these urban-rural divides, but take a similar process, at least, to what Amber relayed throughout her presentation today.
Okay, thank you. Then the next question to Iva, there was quite some interest in the models you presented and then the information you presented. And so there were actually a bit of technical questions to you. First one being on the resolution of the remote sensing that is happening. So what is the kind of resolution, or what kind of ranges of resolution are you working with? And how does that impact sort of the scale at which you are able to model? And then the other question on it, going a bit more into detail on the model, is there also a component including the issue of soil salinity on the yield reduction in the calculations?
Thank you for the question. So in terms of resolution, I'm working for an agency that does yield forecasting at a global scale. And keep in mind that soil moisture is generally a large scale phenomenon controlled by precipitation. So soil moisture in this case is more used to inform foreign agricultural services and the crop analysts of whether there is a change in soil moisture and what will be the impact of that change on vegetation growth and potential yield. So because it's a global forecasting, kind of the goal is global to the global forecasting, currently the data sets that we're using are more in the order of kilometers, between 10 to 25 kilometers. There's no, to the best of my knowledge, a data set that's in the order of centimeters or meters that can be used for yield forecasting. Of course, you can do that using ground-based or aircraft stations. So it depends on the goal and it depends on what questions you want answered. And when you take the global soil moisture products and you combine them with other alternative information sources related to vegetation, such as, for example, hyperspectral data, you can do that convergence of logic where you get information at a final scale than the soil moisture alone gives you. And in terms of the salinity, so the Palmer model is a very simple hydrologic model. It does not account for salinity. I'm sure you can do that at a finer scale or catchment scale using alternative models, but the one I'm working with at the moment does not address that.
Okay, thank you.
Thank you.
Then we had an interesting question, I thought, from Lindsay, our outgoing Parliament President. We heard a lot about the different backgrounds of everybody, somewhat excluding Shana, where I'm just going to say she comes from an environmental policy background back from her studies a while ago. And I guess this question can go out to pretty much any of the three of you. How do you feel your different kinds of background give you different perspectives on the work that you're doing now that you kind of all ended up at NASA in some way? So how does this matter to you, and how do you interact with your colleagues that might come from completely different backgrounds again?
I'll go first. Yeah, as I said, I'm a jack of all trades. I'm not a hydrologist, and that can be challenging going into a field where you're not a technical expert, but it's actually a bonus too. I talked about the wood for the trees. I think for me, it's helped me in many different stages of my career to be able to step back and see the bigger picture, because that helps you think about the right questions to ask and who to ask them of and what solutions might be. So the way I've kind of traversed my path to date, it's not been easy or conventional, but it's allowed me to use my skills. And I'm a storyteller and a scientist, and I think those two things coming together can be very powerful. And as we continue to look down the barrel of the climate crisis, I think more and more people telling their stories and owning their voice is becoming more and more important. And if you can tell a good story about something, you can connect with someone, and connections mean everything. So for me, this marriage of the hard science and the soft science, or the storytelling, you're finding a voice, is critical.
Eva, do you want to go next, and then I'll close this out?
Yeah, sure. So for me, it's been a long journey, which I already mentioned. I did radiate transfer modeling, hydrologic modeling. Now I'm doing applications. So it's been a long journey, and I loved every single step out of it. I second Amber. So I would like to see that what we're doing has a social impact. So getting all of the data, that's perfect. It's great. We have so many data sets, but just storing them on the cloud doesn't mean anything if they're not used. And I guess I met good people along the way that inspired me to look for social solutions and improve decision making of different, make that data useful for other people. I guess that's my big thing. So I kind of like that the connection between the science and the use of what we do and seeing it applied and helping other people get that useful information for them.
Excellent. And so I would say similar things. I mean, it's been a real experience, like wonderful, frankly, experience to work at NASA, because I've always worked at the intersection of science and policy. That's been my background. And I think to be able to have the opportunity to work on that at NASA presents a unique challenge. I mean, often it's a very science-driven agency, but there are a lot of people that want to see the impact of the work that we do. And so I think all of us end up having different variations of that experience as a result. But what's been interesting to me is that I always looked at integrated systems perspectives when it came to science and policies. So it was the nexus of the human dimension and environmental change. So I have a background in environmental conflict and peace building, also on environmental migration and displacement. And so understanding these like drivers of change from a social perspective, and then coming to NASA and seeing how we measure the change from a quantitative perspective really allows for a lot of interesting approaches for better substantiating or supporting the decisions we want to make at multiple levels of governance with science in different ways. And so, you know, the communication element, I cannot stress enough. We are absolutely translators in all that we do, because there is no simple solution to any of this. And I think we want to really make sure that it is a paradigm shift where we aren't just in the habit of giving you a map of something and expecting you to understand it, but really to clear up the entire process we're taking and making sure that it's sustainable, but also relevant to exactly what you're looking for. So I feel like, yeah, that's just different variations of how our backgrounds then get to be translated into this space at NASA. So I'll stop there.
Thank you. With an eye on the time, we're running a little bit late, so I think we'll leave it at that for the moment. Amber already put her email address and a couple of other very nice contact details in the chat, so feel free to follow up if you have more questions on any of these topics. For me personally, I absolutely loved how this session showed that NASA, and of course also other space agencies across the globe, are doing so much more than this sort of cliche idea of space that we have in the back of our head. You know, they're not just bringing us to Mars, they're really also helping us figuring out a life on Earth. They are important actors in the water sector. So there's absolutely nothing weird about NASA being here, because I know that was already a point of surprise for a couple of people earlier in the General Assembly. So thank you so much for being here, all three of you. And to finish off from my side, I also just really want to highlight Laurie's point that you just made in the chat, that you know, we're having a session with NASA, which is probably the most technical session we had all General Assembly long, and all of our speakers are women. I love it. With that, Shana, back to you to close us off.
Thank you, Julianne. Yeah, I think, I mean, I'll just echo everything you said. I feel like, so Julianne is responsible for our session here today. She had the inspiration to invite us, and so we're also thankful to her and her ideas. And so it's just been great. I think it allows us to learn a little bit more about all of you and your interests, while you get to learn a little bit more about us. So all of us have put our emails into the chat box. Please do feel free to reach out if you have additional questions or want to connect in different ways. We're very good at partnerships and networking, and so do feel free to reach out to all of us. But thanks again for all of your time. Thanks to Amber and to Eva. Excellent presentations, and yeah, we look forward to learning more about the World Youth Parliament on Water and all the things that you're doing. Have a wonderful rest of your day or evening.